Okay, this is lesson 1.2, function notation. In function notation, the letter f is the name of the function. So the symbol f of x is the value of function f at a given x value. We read f of x as the value of f at x or f of x. And there's advantages to writing functions using function notation. We'll get into that in a minute. But basically, what we're doing is we're replacing the y in an equation with this notation, f of x. Okay, a function, the way it operates is kind of like a machine. When a value x in the domain of a function enters the function f, the machine produces an output, and that output is f of x. Like if you were putting an x into an equation and getting a y, kind of the same thing. In this case, we're putting in a 2, and what we get is the value of the function at 2, or a number, if it's an equation. The output f of x is determined by the rule of the function, so whatever the rule is. If the rule was 2x plus 1, we'd multiply the x by 2 and then add 1 to get the output, and that'd just be a linear function. So we're going to write a couple functions here using function notation. Our first function, let's name it function f. This is function f, and it's a function of x. So here we go. Let's see if we can come up with the function. A number doubled, subtracted from 12, then multiplied by the original number. So we need a letter to designate number. Since this is a function of x, we're going to use x as our number. So a number doubled would be 2x. And if we're subtracting that number doubled from 12, that would mean we have 12 minus, because it's 12 minus 2x. 2x is being subtracted from 12. And then we're going to multiply this answer by the original number again. And to do that, what we need to do is we need to say, okay, we get our answer for this. I'm going to put it in brackets. And then we're going to multiply by the original number, x. And now what we've created is a function. And if we wanted to expand it, we could write this function in standard form. So let's do that. Use distributive property. X times 12 is 12x. And negative 2x times x is negative 2x squared. And now we have a function in standard form. And it's a quadratic function. Let's try another function. The area of a square as the function of its side length. So in this case, we're working with two variables here, area, a, and side length, L. So when we write our function, there's no sense using f of x because we don't have a function f and we don't have an x. What we have is area and length. So we're going to call this function area as a function of length. So what this means is we're writing an area in an equation, and the only variable we're going to use on the other side is L for length. And the area equation for a square as a function of its side length, if you remember, it's just side length squared. So it would be L squared. And there we have a function of a square with respect to its side length. So what is this function notation? Well, basically it's a fancy way of writing y. Or in the case of this area example, a. Usually we just say a equals s squared to write the equation of the area of a square. But using function notation, we can be a little bit more specific. We can say this equation is the area with respect to a square's side length, L. You could have used S for side length, that's fine too. But A for area kind of made sense, so I used A for area. All right, so let's look at a couple more functions, and we're going to do some evaluating. There's a lot of examples here. We're going to do a couple, and then the others I'm going to leave with you for some practice. As always, the ones we don't do, if you check the course website, there'll be a completed PDF of this lesson with all these done, so you can do a couple extra and then check your answers. But let's do the first one. When we evaluate a function, it means we're going to substitute a specific value of x into the function. And this doesn't change. If this was a regular linear equation or a regular equation, we just replace x with the number and get an answer. But the notation's a little different. So f at 1. What this means is, in function f, replace the x with 1. So I'm going to do that. My function f is 4x plus 3, so instead of x, I'm going to write 1. So it becomes 4 times 1 plus 3. And this is regular substitution like we would usually do. Imagine this just says y equals, and we've just replaced x with 1. The advantage to using function notation is at the very end, you'll know what you substituted, and it will explicitly say it. So if we do a little bit of math here, 4 times 1 is 4, plus 3 is 7. So if I write the f at 1, this tells us that the function f at 1 is 7. And it makes it easier for you to write that point as a solution. Now you could say the point 1, 7 exists and write it as an ordered pair. If you were just using x's and y's, you'd substitute your 1, get 7, then you'd have to look back at the original equation and say, oh yeah, I substituted 1, so 1 is x and y is 7. But using function notation, it's right there. There's your x, there's your y. Let's try B. B says 3 f at 1. And when you have a number next to a letter, it means multiply. So this means 3 times f at 1. Well, we know what f at 1 is. F at 1 is 7. So basically, this just means 3 times 7. But if I write it out and assume we don't know that f at 1 is 7, let's see what we got. This says 3 times the function at 1. So 3 times, and in brackets, I'm going to write what the function at 1 is. The function at 1 would be 4 times 1 plus 3. 4 times 1 plus 3. 4 times 1 is 4, plus 3 is 7, so it is, yes, 3 times 7, and 3 times 7 is 21. So 3 times f at 1 is 21. What if we're substituting a letter? Well, let's try that one. G at a. So this means take function g, and instead of x, replace it with a. So let's do that. Function g is 2 minus 3 times x, but instead of x, we're going to replace a. And now let's simplify, get rid of those brackets. We got 2 minus 3a. So g at a is just 2 minus 3a. That looks a lot like 2 minus 3x, and it is, and it's because we're just switching the letters, basically. We're just switching the x with a when we substitute for a. Just like if we were substituting a number, we'd switch the letter with a number, and then we could do some evaluating. All right. Let's try E. We'll skip D. You can try D on your own. Let's try E. E says h at 2k plus 1. So that means take your function h, and everywhere there's an x, we're going to replace it with 2k plus 1. So here we go. We've got 2x squared. So instead of x, I'm going to write a bracket. 2k plus 1 squared minus 3. And now this is the exact same as this, except the x is replaced with that 2k plus 1 in a bracket. And now we'd have to expand and collect like terms. How do we do that? Well, we've got one bracket squared, and we don't just square both terms. We write the bracket down twice, and we FOIL. Oops, that's not right. 2k plus 1. 2k plus 1. That's 2. Left my whiteout behind. All right, and now we're going to FOIL. We'll keep the 2 out, and we'll do 2k times 2k. It's 4k squared. 2k times 1 is 2k. 1 times 2k is 2k. Both those together is 4k. 1 times 1 is 1. So I skipped a step in my FOIL there. I collected my like terms together and got my 2k. If you break it up, you'll get 2k plus 2k and then add together to get 4k. Now we can distribute the 2. 2 times 4k is 8k squared. Sorry, by k squared. 2 times 4k is 8k, and 2 times 1 is 2. And now we can subtract the 3. And we end up with 8k squared plus 8k minus 1. So what is this function notation? Well, it's just a fancy way of showing what you substitute on the left side as well as the right side, simplifying the right side. And then your answer just shows you what h at 2k plus 1 is. And it's 8k squared plus 8k minus 1. Let's try F. F says f of x minus g of x. So that means we're going to take our original f of x function, no substitutions, and we're just going to subtract g of x. Seems simple enough, but there's a common mistake usually made here. 4x plus 3, and we're going to subtract g of x. So when we subtract an entire function, you have to be careful because you have to put that function in brackets. 2 minus 3x. Because if you don't, you're not going to subtract the entire function, you're just going to subtract the 2. We need to subtract the 2 and we need to subtract the negative 3x. And how that makes a difference, well, here we go. If we subtract 2, we get subtract 2. And if we subtract negative 3x, we get plus 3x, which is different than negative 3x. So you have to be careful when subtracting a whole function. You have to subtract everything, 2 and negative 3x. So we have to use distributive property to do that. Now we can collect like terms. 4x and 3x make 7x. 3 and minus 2 is 1. 7x plus 1. I guess for better notation, you could have put the first thing in brackets and then thought, whenever you're making a replacement, always put it in brackets, and that would be a good way to do it. All right. I'll leave G for you, and you can see if adding is the same. This is a little tricky. This says G of f of x. And what that means is, inside function G, we're going to put function f. So we're going to replace the x's in G of x, so that x, with the entire function f of x. I'm going to show you what that looks like. I'm going to do it in 2 steps. I'm going to write down function g, but everywhere there's an x, I'm going to write f of x. So we got 2 minus 3 f of x. There we go. We took function g, and instead of the x, we wrote f of x. What is f of x? Well, f of x is 4x plus 3. And now we can distribute and collect like terms. Negative 3 times 4. Don't do the 2 minus 3. That's not bad math. Multiplication before subtraction. Negative 3 times 4 is negative 12x. Negative 3 times 3 is negative 9. And now you can collect like terms. Negative 12x minus 7. So that's putting a function into another function. There's another example here, I, that you can try on your own. All right, let's flip the page. Determining the argument of a function, actually solving for x. So here we go. This time, instead of substituting a value for x, I'm telling you what the function equals. I'm telling you f of x is negative 4, and our job is to find x. So it's like I'm telling you what y is, and now you're finding x. So if f of x is negative 4, what we can say is that negative 4 equals x squared plus 4x. We're just writing this down and we're replacing f of x with the actual function. And now if I move the 4 to the other side, I get a nice quadratic. That's factorable. We can factor that quadratic. And factoring is a great way to solve a quadratic. Also, you could use the quadratic formula, but that's a little extra because we just need the solution as efficiently as possible, and factoring is the most efficient way. Numbers that multiply to 4 and add to 4 would be 2 and 2. So we got x plus 2 and x plus 2, but that's the same bracket twice, so we can just write one bracket squared. So the value that would solve this is negative 2. That's our solution. That's our root, or our 0. And we can do the same thing with 5. I'm going to get you to try that one on your own. Set it up exactly like we did this one and then try to factor it. Example 4. If f of x is 2x minus 3 and g of x is 3x plus 2, tell me what x is when the two functions are equal. So that means we're going to take f of x and set it equal to g of x. So in my expression here, wherever I have f of x, the left side, I'm just going to replace it with 2x minus 3. So instead of f of x equals g of x, instead of f of x, I'm going to write 2x minus 3. We're doing a substitution. And g of x, we're going to write 3x plus 2. And now we're just solving. Like terms to one side, I'm going to move my x's to the right side. So we get 3x minus 2 by subtracting 2x from both sides. And I'm going to move the 2 to the left side. Negative 3 stays by subtracting 2 from both sides. And what we end up with is 3x minus 2x, which is x. Negative 3 minus 2 is negative 5. So those functions are equal when x is negative 5. And you could check it by substituting negative 5 into both functions and showing that you get the same value of y. We're not going to do that. But if you want to, you should. All right, that's functions. And this part's a little separate, but I'm going to show you anyways. This is something called a piecewise function. Now that we know what functions are and we know what domain and range are, I can show you something called a piecewise function. And a piecewise function it's a function that's kind of multiple parts. And there are multiple parts over a specific domain. So I'm going to show you what that means. This is our function f of x. And this function f of x has two parts. One part's a quadratic, 2x squared minus 1. And that part exists when x is less than 1. So on the graph, if x is less than 1, it's going to look like a quadratic. And if x is bigger than 1 or equal to, it's going to look like a line, x plus 4. To graph this, we graph both of these and then erase the part that we don't need. And I'm going to show you what that looks like. So we need a ruler and we need to make a scale. I'm going to go 2 boxes up from the bottom here. I'm kind of playing this out in advance. There's my bottom scale. And I'm going to kind of split into the middle here to draw my y-axis. And I'm going to use a box as a box. So each step is 1 on both scales. So here's our y and here's our x. So we're going to start by graphing the first part, 2x minus 1. And if you think of what 2x squared minus 1, if you think about what that looks like, that's a parabola that's been stretched by a factor of 2 and shifted down 1. So its vertex would be 0, 1. 0, negative 1. So I'm going to start by graphing the vertex. And then, since it's been stretched by a factor of 2, that means the step pattern is going to be stretched. So instead of the steps 1, 3, 5, our steps are going to be 2, 6, 10, or double. So over 1, up 2. Over 1, up 6. That's 2, 4, 6. And we won't be able to do the last step, so I'm going to leave my parabola like this. And now I'm going to start to strategically connect it here. When x is less than 1, so that means less than 1, this parabola is actually going to exist. So that means to the left of, here's our 1, so to the left of this point. So that point we can keep. This point we don't actually need. You can draw it if you want, but you're going to end up erasing it. So we do need this part, so I'm going to draw that on there. That's part of our graph. I draw this part on here. But it says less than, not equal to. And the way you can show less than but not equal to is by including an open circle. So right here I've drawn a closed circle. That shows that that point exists. If I erase that point and I draw it as an open circle, that means it goes all the way there, but it doesn't actually include that point. And now what we have is we have a parabola that only exists when x is less than 1, which is the first part of our piecewise function. We're going to do a lot of practice with piecewise functions, so don't worry if this is right over your head. We're going to do practice tomorrow in class, drawing a piecewise function. Let's try the second part. The second part is x plus 4. This is a line that starts at 4, y-intercept, and has a slope of 1. So that's how we're going to graph it. We're going to start at 4, 1, 2, 3, 4 on the y-axis, so there's a point. And we're going to have a slope of 1, so that means over 1, up 1, point. Over 1, up 1, point. Over 1, up 1, point. And I think that's enough points. So I'm going to connect my dots here, thinking about where this part of the line exists. The line exists when x is greater than or equal to 1. So I'm going to draw it. I'm not going to go left of 0 though, because that's less than 0. And we only want greater than 1, so I'm just going to connect this part. Draw a line. And then let's go think about where this part actually exists. Greater than or equal to 1. Well, this is when x is 1. So up here, that point should be a solid point, because it's equal to 1. That's where the graph is equal to 1. And everything to the left of it doesn't actually exist. At that point, at those x's, the graph's a parabola. And now what we have here is a lovely piecewise function. It's this parabola, 2x squared minus 1, all the way until it gets to 1. Then it switches to a line. And this is called a jump. When it's not connected here, we have a jump. All right, that's graphing a piecewise function. Why'd we graph it? Because we're going to do some pretty fancy evaluating here. F at 0. What's f at 0? Well, you can do it two ways. You can look at the graph and say f at 0. Well, 0 for x is here, so where's the graph? Boom, down here, -1. So f at 0 is -1. Or you can use the equation. You can say, okay, f at 0 when x is 0. That's not greater than or equal to 1, that's less than 1. So I got to plug 0 in here. 0 squared is 0, times 2 is 0, minus 1 is -1. You can use the equation or you can use the graph. It's up to you. So I want you to try to do f at 1, f at 2, and f at -2 plus f at 5. Using the graph or using the equation. Up to you. All right, thanks for watching lesson 1.2, and I'll see you next time.